These are the notes for AP Calculus on the topic of common Maclaurin series. So there's 4 Maclaurin series, or Taylor series, the more general term, that you need to memorize for the AP exam. That if you don't, some problems that could be really quick would take a really long time a lot of times. So let's look at them and see what could help us to make it easier to memorize these. So let's start with cosine of x. So these are power series and specifically Maclaurin series. Notice centered at x equals 0. So cosine x. And then over here it has the interval convergence. For what x values does this cosine converge? And here it converges everywhere from negative infinity to infinity. So the way I think might be easiest to remember cosine is if you remember the graph of cosine. So do a little sketch here. So if we sketch what y equals cosine x looks like, cosine, remember, starts up here at 0, 1, and curves down like this, back down to -1, back up to 1, same thing the other way, and it keeps on going both directions. So notice, based on the symmetry, this is symmetrical about the y-axis. And remember, for functions like cosine, which is a function, when it's a function symmetrical about the y-axis, that's referred to as an even function. So let's take a look at our pattern here. Well, notice we have all the even exponents. That's not a coincidence because cosine is an even function. That's where the name even comes from, for polynomials that just have exclusively even exponents. And you might think, well, what about this 1? I don't see any x's there. There really is an x. This is like 1x to the 0. And 0, remember, is an even number. If you divide 0 by 2, it does divide evenly to 0 and 0. Notice another feature about this. Notice it follows the same pattern as our Maclaurin series. It's just missing all the odd exponents. It doesn't have x to the first, x to the third, x to the fifth, because it's an even function. That's why I remember it. And then notice here, it's also alternating, positive, negative, and so on. And the reason why it's alternating is because if you look at the graph, cosine does alternate between positive and negative, doesn't it? So wouldn't that make sense that the series that equals cosine would also have to alternate between positive and negative? And it does. So what's causing that to alternate in our formula for the general term, notice, is this -1 to the n power. That's what indicates it's an alternating series. Notice if you substitute in 0, -1 to 0 is 1, so that's positive. If you substitute in 1 for the next term, -1 to the first is negative, so that means the first term is negative. If you plug in, this next term is negative, I should say. If you plug in, substitute in 2 for n, -1 squared is positive, then 3, negative, and so on. So that's what causes it to alternate. And notice the pattern here, because all the exponents are even, that's why we see x to the 2n. When you substitute in 0, you get x to the 0. Substitute in 1, you get x to the second. Substitute in 2, you get x to the fourth. 3, you get x to the sixth, and so on. And that same exponent, notice, appears on the denominator in parentheses, 2n factorial. So when you substitute in 0, you get 0 factorial, which is 1, so you don't see that there. And then substitute in 1, 2 factorial, 2 gives you 4 factorial, 3 gives you 6 factorial. Notice that is not the same as this. Looks the same almost except for the parentheses, but that parentheses makes a difference. Here it'd only be that n factorial and then times 2. The 2 doesn't get applied to the n before the factorial. Here you multiply by 2 first and then the factorial of that. So that is not the same there. So be careful about that. And then plus dot, 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 that shows it goes on forever. It's an infinite series. All right, so in a similar way, let's look at the Maclaurin series for sine x. Again, we want to have these memorized so that we can adapt them as needed. Also converges from negative infinity to infinity. So an easy way to remember this one, again, just remember the basic graph of sine. Similar to cosine, except for sine, remember, sine of 0 is 0, so it goes to the origin. And still goes between -1 and 1, but it curves up to 1, then down to -1, and then this this way it goes down to -1, back up to 1, and so on. So that's the graph of y equals sine x. Notice it also alternates between positive and negative, which is a reminder of why our series, Maclaurin series for sine, also alternates between positive and negative. Notice just like cosine, it starts with a positive term, which is why you see this -1 to the end there. That also indicates it's alternating. But now, notice the graph of sine is symmetrical about the origin. And for functions, remember that's referred to as odd. Well, why is it referred to as odd? Is because functions with only odd exponents are symmetrical about the origin. And that's what we see here. This is x to the first, x to the third, x to the fifth, x to the seventh, and so on. Notice because the exponents are all odd, that's why you see x to the 2n plus 1 in your general term. That way when you substitute in 0, you get x to the first, which is the first term. When you substitute in 1, that's 2 plus 1 is 3. Substitute in 2, 2 times 2 is 4 plus 1 is 5. Substitute in 3, 2 times 3 is 6 plus 1 is 7. So you can see by adding that plus 1 to the 2n, now it means all the exponents of x will be odd. And notice it's divided by that same factorial, 2n plus 1 factorial. We don't see it on this one because when you substitute in 0, that's just 1 factorial, which is just 1. And then finally, or not finally, I should say, the next one we see e to the x. Again, if we skip, notice all these first three converge from negative infinity to infinity. Again, if we think about the graph of e to the x, that can help us remember it's Maclaurin series. Well, e to the x, remember when you substitute in 0, is 1. So it goes, so y equals e to the x, looks like this. It's not symmetrical about the origin or the y-axis. It looks like this, standard exponential graph. Notice it never gets to 0 there. So notice all the y values at e to the x are all positive. It doesn't alternate like sine and cosine, and that's an easy way to remember why all the terms in e to the x are positive. It's not alternating, so we don't see that -1 at the end of the general term. And another thing you can do to remember it, it's kind of like sine and cosine put together, which you might not expect, but see in the power series it's got both the odd and even terms in the Maclaurin series, which is why the formula for the general term is a little simpler. It's just x to the n. You substitute in 0, you get x to the 0 right here, which is 1. Substitute in 1, you get x to the first, 2, x to the second, and so on, and now divided by that same factorial. We just don't see the 0 factorial and 1 factorial because those are both equal 1. So just remember, it's like having sine and cosine together, just except all the terms are positive. And the final one, you may not know what the graph of 1 over 1 minus x looks like. So this one actually follows a pattern that we've already looked at earlier this year. So if you look, well, 1 plus x squared plus x cubed. Well, and notice it only converges between -1 and 1. Okay? Well, unlike the other ones, which always converge for all x values. Well, let's think, what else converged when something was only between -1 and 1? And look at the pattern. What's happening? Every time to get the next term, notice you're multiplying by x. Anytime you're multiplying by the same thing to get to the next term, remember that's really represents a geometric series. And that's what this is. It's a geometric series. And their common ratio here, notice every time you're multiplying by x to get to the next term, so their common ratio is x. So that common ratio x, remember, in order to converge for a geometric series, does have to be between -1 and 1, which is what that says. And where this is coming from, the reason why it equals this, if you remember your sum of a geometric series, remember, in an infinite geometric series, it's the first term a sub 1 over 1 minus the common ratio. But in this case, our first term, a sub 1, is 1, so that's why it's a 1 there. And the common ratio we just saw, r, is x. So this is really just coming from the sum formula for a geometric series. So this is really a geometric one that we've already seen. Key is to recognize it as just, in this case, 1 over 1 minus x to find what it equals. Okay, so these are the 4 you want to make sure you have memorized for the AP exam. Again, to save us a lot of time, make some problems Much easier than they would be if we didn't have these memorized. So let's take a look at some of the example problems now. All right, this first one says the function f has derivatives of all orders. Okay, so the derivatives exist everywhere. And h of x is sine of x cubed. And we're asked to write the first four non-zero terms and the general term of the Maclaurin series for h about x equals 0. Remember, all Maclaurin series are about x equals 0. Right, so it's all Taylor series. All Maclaurin series are Taylor series, but they're specifically about x equals 0. Taylor series don't have to be about x equals 0. So notice, if we didn't have sine of x memorized, this would be kind of a beast of a problem, because you'd have to take, in the pattern, right, you'd have, on the Maclaurin series pattern, we'd have the original function. And to get the first four non-zero terms, we'd have to at least take the derivative 3 times. H prime of x wouldn't be that bad. You just use the chain rule, and you get cosine of x cubed, derivative outside, times derivative inside 3x squared. But then notice, to get the second derivative, you have to use the product rule, and then there'd be 2 terms. To get the third derivative, you have to use the product rule twice. So it's doable, but it's very time consuming. Thankfully, if we have sine memorized, the Maclaurin series memorized, we can just adapt it. Because notice, the only difference is we've got x cubed there instead of just x. So if we look back at sine, remember sine is the odd function there. So it has all the odd exponents. So normally, sine x would be x to the first. Just to follow the pattern, you can see this is over 1 factorial. Minus, it's alternating, x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus, and the general term would be x would be alternating, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. That's for sine x. So I just rewrote what we already wrote down here. Okay? However, all we have to do now for sine of x cubed is just wherever there's an x, replace it with x cubed. So this would be x cubed to the first over 1 factorial minus x cubed to the third over 3 factorial plus x cubed to the fifth over 5 factorial minus x to the x cubed to the seventh over 7 factorial plus, when I forgot to put the plus dot dot dot, keeps on going forever. Then when we do this, the negative 1 is not going to get affected, negative 1 to the n, x cubed to the 2n plus 1 divided by 2n plus 1 factorial. Plus dot dot dot, and then if we simplify that, here's our first 4 non-zero terms. So x cubed to the first is just x cubed divided by 1 factorial. So it's just x cubed minus, that's going to be, remember we have exponent to another exponent, you multiply them, so that'd be x to the 9th over, now you could work out 3 factorial. Sometimes it's worked out, sometimes it's left in factorial form. In this case, I notice nothing's going to reduce here. There's no constants on the numerator here. And 7 factorial is going to be rather large, so let's just leave it in factorial form in this case. If it was reducible or a little smaller factorials, I might work it out. Either way is correct. It's just if it's multiple choice or if there's something else you have to do with it, sometimes having it worked out might be a little easier. I get it to work. So just leave this 3 factorial plus x to the 15th over 5 factorial minus x to the 21st over 7 factorial plus dot 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 plus, then we have negative 1 to the n. And notice here, just like we multiplied these exponents, we'll do the same thing here in this general form. So you have to multiply 3 by this whole exponent of 2n plus 1, so the 3 distributes to both terms. So that's going to become x to the 6n plus 3 over divided by 2n plus 1 factorial plus dot dot dot, so it keeps on going forever. Then if you're not sure if you have it right, you can always test it. If we substitute in 0, we'll get x to the third That'll be positive x to the third over 1 factorial, which is just 1, so we get that. If you substitute in 1, you get x to the ninth over 3 factorial, and that's going to be negative, and so on. So this is the correct general term and the first 4 non-zero terms of our Maclaurin series. The other thing that would make this difficult is you might get some terms, if we did it this way, we might get some terms that are 0 as well. Every time you have sine of 0, that's going to be 0. So it could take a really long time to figure this out using, if you didn't have sine of x, the Maclaurin series memorized. All right, let's take a look at the next example. This one a little more complicated. We've got f of x is 1 minus cosine x over x. You can see if we did it the long way, we'd have to take the first derivative using the quotient rule, and then it'd keep getting more complicated after that. But thankfully, we don't need to do it that way because we'll have cosine of x memorized here. The first 4 non-zero terms, again, and the general term. This time they call it a Taylor series, but since it is about x equals 0, it's really also a Maclaurin series. And they might call it either one. But the Taylor series, again, we'll see later, don't have to be about x equals 0 Maclaurin series do. It's a specific type of Taylor series. It's this Maclaurin series. So here what we have is 1 minus, and then right here, this is where we can put, where we have cosine memorized. And cosine, remember, is an even graph, so it's going to have all the even exponents, starting with x to the 0. But x to the 0 is just 1. And then remember, cosine, just like sine, alternates, so the next term would be negative. And the next even exponent after x to the 0 is x squared, and over 2 factorial. And it alternates to positive, next even exponent, x to the 4th, over 4 factorial, and then alternates to negative, x to the 6th, over 6 factorial. Now let's think about this. If we want the first 4 non-zero terms, you might think, well, that looks like enough, that we've got 4 terms there. But if you think ahead, notice what's going to happen here with these 1s. This 1 minus 1, the others are going to cancel out, leaving you with 1, 2, only 3 terms. So because of that, we have to go a little further and then say plus the next even exponent, x to the 8th over 8 factorial, and then we'll put plus dot dot dot. Then remember our general term here, it's alternating. So we have negative 1 to the n, cause it to alternate. Then we've got the even exponent, so it's x to the 2n divided by that same even exponent in parentheses, factorial. Okay. So we've got 1 minus that. Okay. And then, don't forget, it's all divided by x. Okay, so let's simplify the numerator first, then we'll worry about the dividing by x. So first, these 1s are going to reduce out, right? 1 minus 1. Those are gone. And then don't forget, though, this negative applies to this whole thing since it applies to cosine. So we have to distribute the negative to the rest of these, which is going to change the sign of all of them. So this negative x squared over 2 factorial now becomes positive x squared over 2 factorial. The positive x to the 4th over 4 factorial, distribute the negative, now becomes negative, and so on. Then it's going to be positive x to the 6th over 6 factorial, negative x to the 8th over 8 factorial, plus dot dot dot, our general term. Well, think about what happened here. We multiplied these all by negative 1, didn't we? But here there's already a negative 1 in the formula for our general term. So what do you think that's going to do to it? Well, we've really got negative 1 here. We have negative 1, which is like to the negative 1 to the first, times negative 1 to the n. Well, when you multiply, just think like x squared times x cubed gives you x to the 5th, right? And how do we get that 5? We added the exponent. The same thing would happen here, so that would give you negative 1 to the 1 plus n, or n plus 1. So that's what our form is going to look like now, negative 1 to the n plus 1. Okay, and then x to the 2n over 2n factorial. So that would be our first 4 non-zero terms and general term if we just had 1 minus cosine x. But don't forget, there's one more thing to do. This whole thing is divided by x. So what's that going to do? That means we can divide each of these by x. Well, if you divide by x, one of the x's is going to reduce out. So that's now going to become x to the 1st, or just x, over 2 factorial, minus x to the 3rd over 4 factorial. plus x to the fifth over 6 factorial minus x to the 7th over 8 factorial plus dot 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 negative 1 to the n plus 1. Now look at what I did to the x's, right? When we divided by x, it subtracted 1 from the exponent of x. So wouldn't it make sense that the same thing is going to happen here? When we divide x to the 2n divided by x, it's going to subtract 1 from it, so it becomes x to the 2n minus 1. Over the denominator, factorial didn't change, so that stays 2n factorial. Plus dot dot dot, so it goes off to infinity. Okay, now, something happens here. This is correct. These are our first 4 non-zero terms and the general term. But occasionally what happens when you modify this, notice if you plug in 0, that's going to look like negative 1 to the first. That's negative 1. You'd have x to the negative 1 over 0 factorial. We don't see that one here. So sometimes what happens when you modify it, it sometimes will change the starting end value. That's what's happening here. In this case, since 0 doesn't give us that first term, there you can see x actually 1. If you plug in 1, you'll have negative 1 squared, which is positive. Our first term is positive. If you substitute in 1 here, that's 2 minus 1, so x to the first, which is what we have. And substitute in 1 here, that's 2 factorial, which we have. Then if you substitute in 2, it'll be negative 1 to the third, which is negative. We see that second term is negative. Substitute in 2 there, that's 4 minus 1, that's x to the third, which we see right there. And substitute in 2 there, we get 4 factorial. So it just changes the starting end to be 1 instead of 0. Again, same series. It's just that those are the two most common starting values for n. You'll see is 0 and 1 in our series, and just happen to change it in this case. And that's really because the 1s here ended up canceling out. All right, let's take a look at the next example. This one, we've got, again, the first 4 non-zero terms and the general term of the Taylor series about x equals 0. So again, since it's about x equals 0, it's really also a Maclaurin series. Derivatives of all orders, the derivatives exist everywhere. This one wouldn't be too bad if we did it the traditional way, because we'd have to just keep using the chain rule over and over again. The derivative e, that e part stays the same, so that wouldn't be too difficult. But it's even easier if we remember the e to the x one. So look at what we've got here. So remember e to the x, the pattern here. It's not alternating, they're all positive, and it's like having sine and cosine together, so you have all the terms. So it'd be 1 plus x to the first plus x to the second over 2 factorial plus x to the third over 3 factorial, and then so on. And then the formula for it is just x to the n over n factorial. So that's e to the x, but we have to modify this in 2 ways. Notice instead of x, we've got negative x over 2 in place of the x, so we'll have to replace all the x's with that. And we've got a 5 on the outside multiplied by for those two things. So we'll have 5 times, I'll put a big old parentheses there. And then if we substitute in negative x over 2 for all the x's, well, the 1's not going to change. But instead of x, that'll be negative x over 2 plus negative x over 2 squared over 2 factorial plus negative x over 2 cubed over 3 factorial plus dot 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 plus, we'll substitute in here as well, negative x over 2 cubed over, sorry, not cubed, to the n over n factorial plus dot dot dot. And again, that whole thing is multiplied by 5. Let's first simplify inside the parentheses, and then we'll distribute the 5 at the end. So this first one is just going to be 1. That doesn't change. And this is going to be negative x over 2. This is going to be, well, negative squared. Negative 1 squared, that's going to make it stay positive. And then just think, if you square this 1/2, we'll have x squared, obviously, on there. But let's see what it's over here. If you square that, that's going to be 1/4, right? But you're dividing by 2 factorial, which is 2. 1/4 divided by 2, that's 1/8. So you'd have x squared over 8. This is negative 1 cubed. That's going to make this one negative. 2 cubed is 8, so that's 1/8. Divided by 3 factorial, and 3 factorial is 3 times 2 times 1. So 1/8 divided by 6, that's like 1/8 times 1/6. So I give you x cubed from right here over 8 times 6 is 48. First four non-zero terms, that's going to give us those. We'll just multiply by 5 plus here. Distribute that out. We've got a few different things. We'll have, easier to write in this case, we've got -1 to the n. We've got x to the n. And the denominator, we've got 2 to the n. Okay. And then divided by n factorial, that's like multiplying by 1 over n factorial, so that n factorial just stays in the denominator. And then we're multiplying these all by 5. So this becomes 5 minus 5x over 2 plus 5x squared over 8. Oops. Minus 5x cubed over 48. There's our first four non-zero terms. Plus, well, it just multiplied these all by 5, so it'll do the same thing with our general term. So it's just going to be 5, -1 to the n, x to the n, over 2 to the n, and factorial. Notice you can't distribute the 5 with a -1, -5 to the n, because then that would mean you'd be raising 5 to the nth power, so these wouldn't stay 5, it'd be 5, 25, 125, which doesn't happen. So it just has to stay separate like that. So there would be our first four non-zero terms and the general term for that Taylor series or Maclaurin series. All right, let's take a look at the next one. So sometimes they may not use one of those four that you expect to memorize, and instead they'll give you one which they don't expect you to memorize, but they'll tell you what it is. Sometimes they'll write in summation notation. Sometimes they say the Maclaurin series for natural log of 1 plus x is x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4 plus, and they give you the general term right here. So they're giving you the whole thing because they don't expect you to have natural log of 1 plus x memorized. And then they're saying f of x is natural log of 1 plus x to the fourth. Very similar to this, except notice one key difference. X to the fourth is in place of x. So again, it says write the first four non-zero terms and the general term of the Taylor series about x equals 0, which again is a Maclaurin series, really. So just like the other ones, we have to modify it. Wherever there's an x, it gets replaced by x to the fourth. So we'll have x to the fourth in place of that x, minus x to the fourth squared in place of this x, divided by 2, plus x to the fourth cubed over 3, minus x to the fourth over 4, plus, and then -1 to the n plus 1, x to the fourth to the n over n. And then we can just simplify that a little bit. So we get x to the fourth minus x to the 8th over 2 plus x to the 12th over 3 minus x to the 16th over 4. There's our first four non-zero terms. Plus -1 to the n plus 1, x to the 4n over n. So you modify it in the same way, it's just they give you one, you're modifying instead of having to use one you've memorized. Again, if you want to check to see if it works, you could try plugging in 0, but then notice divide by n, plugging in 0, that's not going to work, is it? So this is one where you actually start 1. If you plug in 1, notice it'll be -1 to the second, which is positive. First term is positive. Plug in 1 there, that's x to the fourth, divided by 1. Substitute in 2, you get -1 to the third, which is negative, so the second term is negative. Plug in 2 there, that's x to the 8th. 2 there, that's 2. So you can see that form of general for the general term does work. Okay. Now let's take a look at if we are given one where they tell you the sum, or basically asking you for the sum of this series, is which of the following. Okay. This is another one where they really expect you to have those first four memorized to figure this out, to know which one it goes with. You don't really have time on the AP test to derive each of these options here. So look at what we have. Well, it's alternating, right? And you can see the exponents are even. Notice that this fits the pattern for sine, sorry, not sine. The one function that's even is cosine. Sine is an odd function, right? So this is the pattern for cosine x. But notice we don't see the x because the x would usually be right here where all the e's are. So that's your clue that it's just cosine of e. It fits the pattern for cosine. Just e being plugged in for all the x's. And that's it. If it was sine, you'd see the alternating pattern with the odd exponents. If it was e to the e, you'd see it all positive, not alternating with no missing terms. And if it was 1 over 1 minus e, you would see, well, this one actually would diverge because e is not between -1 and 1. The common ratio would have to be between -1 and 1 to fit the pattern there. So in that case, if this fit the pattern for 1 over 1 minus x, it would actually be non-existent if e was plugged in, because e is not about 2.7, it's not between -1 and 1. All right, and that concludes the notes for AP Calculus on the topic of the common Maclaurin series.